is Ulrich Pennig, who will tell us about equivariant high-acoustic field theory.
Okay, thank you very much. I should say this is joint work with David Evans from Cardiff University, based on the stuff that I worked out with together with Marius Dadarlat from Purdue. And thankfully, Andre Enriquez did a good job at explaining what our theorem is about. So let me just shortly repeat the non-equivariant case. So non-equivariantly, one of our theorems said that if I look at the classifying space of the automorphism group of this Kunst algebra O infinity turns out with the compact operators, then this has the homotopy type of this space BGL1 of, and Andre used the notation K underline, I guess. And there is a slight generalization of this result just by using different strongly self-absorbing C-star algebras here. And one choice that you could take is you can tensor this O infinity with the infinite tensor product of some matrix algebra, for example. So you could take Mn infinity. So this is my notation for an infinite tensor product of the n by n matrices tensored with themselves infinitely many times. Tensor O infinity, tensor K. This is also strongly self-absorbing. It's also a Kirchberg algebra. If we can determine the homotopy type of that, the thing that you get is this is BGL1 of K-theory, of the K-theory spectrum, but now localized or with n inverted. So this is, so you take K-theory, and in a ring you can invert multiplicative subsets. You invert the multiplication by n. And this is still a very complicated C-star algebra there, but this one is really easy to handle. So you could also ask, what is this? And there's an obvious map from this space to that. If I just look at the automorphisms, I can take an automorphism of this algebra and tensor it with the identity on O infinity, which gives me a group homomorphism from the automorphism group from here to there. So I get a map on classifying spaces here. And one thing is that since this is a strongly self-absorbing C-star algebra in its own right, this is still an infinite loop space. So in particular, it corresponds to a spectrum. I can work out what the cohomology theory underlying it is, or that you obtain from this is. And it turns out that it's not that much different from this theory. You just have to take into account that since O infinity destroys the order structure on K-theory, that's the reason why you see all units here. The only things that you don't see if you're using this algebra is something that comes from pi 1. So this is an iso on all pi n except on pi 1, where it induces the map from GL1 of K0 m n infinity plus into all of the units. So what is this? K0 of mn infinity is just the group Z with n inverted. So this is, and you can also see the ring structure since this is strongly self-absorbing. And this plus here just means take, well, basically just the intersection with the positive rationals here. So you take the positive elements in here. And this on pi 1 includes, this is still a group with respect to multiplication. And then you just take the inclusion. That's what happens on pi 1. So you don't see all of the units, you have something in pi1 that you have lost, but this algebra might be easier to handle. Okay, and now about equivariant twists of K-theory. So one of the benefits that you could get from this explicit description as locally trivial bundles is that you could, I mean, it's hard to define what you mean by equivariant twists for these H3 twists. It's easy because there is a definition of equivariant H3. So what are G equivariant twists? Of K-theory, and for the twists that are classified by third cohomology, you have nice models for those. For example, you could take G equivariant bundle drips this has been worked out, I think, by Murray, Roberts, Stevenson, and Bossel. And you could also take the approach that Attia Siegel in their paper about twisted K-theory chose. You can just look at G equivariant bundles of compact operators.
What is G for you here?
Oh, yeah. So in the examples that will follow, G will be a compact Lie group. Could also be a finite group, well, which is contained in that. But I mean, having this model for the non-equivariant twist, it's very tempting to just say, well, G equivariant higher twists should be, so idea, just take G equivariant bundles with fiber D tensor K for D strongly self-absorbing. Right? This is what's sort of suggested by this model. And what I didn't tell you so far is why you should care about G equivariant twists of K-theory at all. So
you want to exclude G acting trivially on fibers?
Do I want to exclude that? I don't know, at this point, not. So let me state a motivation for considering G equivariant twists and also G equivariant higher twists maybe. There's a nice theorem by Fried, Hopkins, and Telemann. Which says in particular the following: if I have a simply connected compact Lie group, and if I look at the smooth loop group, then the statement is, if I look at the representations at a certain level of the loop group. So what is this? This is the Wallinder ring of positive energy representations of Lg at level k. Then you can express this using twisted K-theory. So this is isomorphic to the twisted K group, the equivariant twisted K group of G, where I consider G as a G space with respect to the adjoint action. And so this is the degree I'm looking at, and there's a twist involved, and the twist is related to the level that I'm considering here. So this is twisted equivariant K-theory with twist tau of k depending on the level of k.
Well, I'm a little confused that you ask this question, or that you somehow indicate that there's a choice. I mean, once you fixed, what you want to think about what equivariant K-theory is, then at least one side of the thing is, now you want equivariant bundles of K-theory spectra, which are modules over. If you fix this side, then there's no choice. So the question is, what is your choice for equivariant K-theory, and what kind of bundles you want to model? K modules over usual unequivariant K-theory, or over. Then you don't have any choice, and the question is answered. You have to just to fix your setup. What is equivariant? The basic.
Right.
Then the question is maybe how you can analytically represent these twists, but what the twist is unclear.
Okay. Yeah, that's true.
That's why what is your choice?
But okay, can we? We'll have a long answer that requires probably another talk. If I have G equivariant bundles, then I can still associate these bundles of strongly self-absorbing C-star algebras to that, and that would be my definition of equivariant twisted K-theory. If I have such a bundle, and all of this is equivariant, then I get an action of the group on this space. I will take that. And this is equivariant. So this is functorial for equivariant maps between trees. This is what I would call higher equivariant twisted K-theory. I don't know if you're happy with that definition, but that's at least one thing that you can do. If you're aware of the fact that, you're doing analytic things here because you're taking the cross product with G, so this might not work if you have infinite discrete groups, for example. Okay? But the question that I so here you have an explicit construction of this twist that you have here. For example, you have a construction as this basic equivariant gerb over the group, And from this, you might be motivated to ask, are there any interesting examples of equivariant higher twists over a compact Lie group G? And this is what, I mean, this project is sort of about. It's also, I should say, it's a lot of this, or all of this, is work in progress. So I should have handed out safety goggles. This might explode in front of you. So, but I want to give at least constructions of what I think should be examples of equivariant higher twists, if you believe this definition with equivariant bundles and taking cross products. Well, he's not bleeding, so so to construct these, I need some more preliminaries about C star algebras. Preliminaries about C star algebras and Morita equivalences. So one interesting notion for C star algebras is that of Morita, I should say Morita-Riefel equivalences, which works as follows. So if you have two C star algebras, I can look at modules over, well, the second, for example, of this one. So, and the right notion of module that you have in the context of C star algebras is that of a right Hilbert B module. This is nothing too frightening. What you should think of here is you should think of the definition of a Hilbert space and replace the complex numbers, so the scalars, by B. And then what you end up with is a Hilbert B module. So in particular, you have an inner product which takes two vectors and spits out an element in B. And another thing that you get from this is you can look at the right notion of bounded operators from E to E. So you have bounded operators and if you have bounded operators in inner products, you can also define compact operators as the closure of the finite rank operators. So you have compact operators. So these are bounded B linear operators, and they also, the crucial property that they in addition have is that they are adjointable with respect to this inner product. So you have compact operators as well. And suppose we have an isomorphism phi from A into the compact B linear operators of E. Then this pair, we call this pair a Morita-Riefel equivalence. So E I will often suppress the phi from the notation, is called a Morita-Riefel equivalence. Between A and B. And this is really the right notion of an A-B bimodule, basically. So, and if you have this, then one thing that you can do is you can also define an A-valued inner product on E. And since this is an isomorphism, there's also a way to, so this is an A-B bimodule, meaning that this gives you a left multiplication by A, and it already had a right multiplication by B. You can reverse that, so we have an opposite bimodule. Which is just defined as the compact operators from E to B considered as a Hilbert B module, right Hilbert B module. And this is a right Hilbert A module and it comes with an isomorphism from B to the compact operators on E up, which makes everything very symmetric. And we have that the inner product also induces an anti-linear, so conjugate linear isomorphism of, well, Banach spaces, basically. So you have this flat isomorphism from E to E up, sending a vector psi in here to forming the inner product with psi. And also there's a tensor product of A-B bimodules with B-A bimodules over B. So, and we have canonical isomorphisms if I take E, which was the right Hilbert B module, tensor that over B with E up, this is isomorphic to A as an A bimodule and works in the other direction as well. And one thing that you can do when you have a Morita equivalence is you can form the so-called linking algebra. And this looks as follows. So you take matrices of the following form. You put A into the upper left-hand corner. You put E here, E up here, and B here. And the multiplication, the matrix multiplication in this indeed makes sense. So if I want to, 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 if multiply two of these things, I do whatever I can do. So for example, here, I can multiply the A with A prime, and then I have the xi and flat of eta prime. I can take the inner product of that. So in this corner, you would have A prime plus the inner product xi with, not flat, this one. That you want to end up in A, so you need to take the A-valued inner product. And in the off-diagonal entries, you have A times xi plus xi times B prime, for example. Oh, A times xi prime plus xi times B prime. And then you keep going. So this, you can equip this with a norm, which it inherits from representing it on a right-Hilbert B module, for example. And you also get a star on this. So this is a C-star algebra. And there's another way to write this. Maybe I squeeze that in here. So I can take the following groupoid. I take the groupoid with two objects, 0 and 1, and I have two morphisms such that their composition is the identity on the corresponding object. And I can look at the following bundle over this groupoid. Where the fiber over the object 0 is A, the fiber over the object 1 is B, the fiber over the arrow from 0 to 1 is E, and the fiber from 1 to 0 is E op. And I look at the algebra of sections of that, and what I end up with is, so I can multiply these sections, and the way they multiply is precisely the way that I have described above. So the section algebra of that would be the linking algebra. Okay, I should say that this is not the only. I don't have just this bundle. I also have a multiplication. I forgot that. Sorry. I have a multiplication of elements in E that is compatible with the groupoid composition here. So plus multiplication in E covering the composition in G. And this is something that you can vastly generalize to the notion of a fell bundle. And I will give you a slightly sketchy definition of this. So if I have a locally compact groupoid and define this to be the set of composable arrows, then a fell bundle is the following thing. A fell bundle is a bundle of Banach spaces. So this is a Banach bundle. Which is something that is different from topological bundles. So this is a surjection, an open surjection, such that the fibers are Banach spaces. But if I look at the topology on the E is such that if I take the norms of the elements, then the norm map is continuous. And also all of the addition is also continuous. The scalar multiplication is continuous. And there's another weak continuity condition, but this is often far from being locally trivial. So this is something that you have, but you also need this multiplication. So you have, if you define E2 to be all of the elements that you should be able to multiply, so this is the set E0, E1 in E times E, which map to composable arrows, so that's such that Q E0, Q E1 is in G2. Then E is a Fell bundle if we have a multiplication, which is a map from E2 to E, and a star from E to E. And this should be, well, it should have all the properties that you want. It should be associative, fiber-wise, bilinear. And it should cover the multiplication of in G. And this should covering, so this should be covering the inversion map on the groupoid and should be fiber-wise antilinear. And, well, you have more conditions. So the norm should be submultiplicative. And you have a C-star norm condition. And you want E star E to be positive, which makes sense because all of the conditions ensure that if I look at the fibers over an object, so over the identity of an object in the groupoid, then this will be a C-star algebra.
Is the same as a groupoid internal to C-star algebra, such as the object space is a commutative space?
Such that what the
object space is commutative? I mean, because the star is we have separable C-star algebra. Groupoid in C-star algebra is commutative.
Yeah, I mean, what this wants to be is, I mean, it's like a C-star category that's parametrized by a space in a way.
Yeah. This is
Yeah. Okay, if we're now talking about the same thing, then it's probably true. And we call, the notion, I should explain what saturated means. If whenever I take the linear span of all the products of two of the E's, this sits inside EG1 times G2 by definition, because the multiplication covers the groupoid multiplication. And if this is dense in norm, So by this I mean the linear span of all the products. Then this is called saturated, and what this being saturated implies that if I look at, oops, change the notation. That if I now look at the fiber over one of the group point elements, this is Morita-Riefel equivalence between the source and target C-star algebras. And one thing that you can do whenever you have such a Fell bundle is you can associate to that a C-star algebra of sections. So there you can take the sections and close them off in actually more than one way. So you get where if the groupoid is nice enough, so you need a Haar system on the groupoid. So you have a reduced Fell C-star associated C-star algebra to this Fell bundle, and you also have a maximal C-star algebra associated to this Fell bundle. Okay. Start. So what does this have to do with these notions of equivariant bundles with fiber mn infinity tensor K? So one thing that happens is if you take a Fell bundle over, so if you have a topological space and choose an open cover of that and take the Czech groupoid associated to that open cover, and then take a Fell bundle such that the fiber C-star algebras that you have over the objects are just the complex numbers, then what you get from this multiplicative structure is you just end up with a gerb over the covering. So that is why I think this is kind of the right non-commutative generalization of gerbs, because here what you are doing is you're replacing the complex numbers here with bimodules over or with Morita equivalences over C-star algebras. So let's look at the following example. So you have the circle acting on the circle trivially. And now we can look at the equivariant K-theory of a point. So this is the representation ring of the circle, which is the polynomial ring in T and T inverse. And now I can pick a polynomial in this representation ring. And I need it to be positive so that it is really represented by an element in the, by a representation and not only by a formal difference. So I need it to have non-negative coefficients. So for example, Q could, I just need to give the coefficients some names. Q could look like this. And then, as I said, I did this, I chose these non-negative coefficients because now I have a representation on c to the n which realizes this polynomial. So I have a representation like this, where rho I of z is just the direct sum of the ith character. So I have ai copies of psi I, where psi I is thus just this thing. And one thing that I can do is I can take A to be the associated infinite tensor product of matrix algebras. Which is strongly self-absorbing. And this is also a T algebra. And you can work out what the K-theory of this is. K0 turns out to be the representation ring of the circle, but with this polynomial Q inverted. That's because this is the co-limit of over each of these matrices. This is basically because the action that I have on this is a product action. So it acts on each tensor factor here by the adjoint action with respect to this unitary. And if you work out what this does in each step of the co-limit that's used to form these algebras, it is given by multiplication with this polynomial. So that's what you invert. And the thing is, we have an equivariant Morita equivalence that induces multiplication by Q. Oh yeah, by the way, this is 0 on the equivariant K0. And this Morita equivalence is just given by C to the n tensor A, where the right multiplication is just A multiplying from the right on A, and the left multiplication is Y an isomorphism psi from A to M and C tensor A. So since this was constructed basically just to absorb these kinds of C-star algebras, there's an isomorphism like this that is induced by shifting the factors. So induced by shift. In particular, this is also T equivariant. So now, I can cover the circle by two open sets. Call this U0 and this U1. I can take the Čech groupoid of this open cover. So G, the space of morphisms, is just all the intersections, and the space of objects is just UI. And I have a Fell bundle E over G just by mimicking what I did with the linking algebra. So I define E to be A over U0, 0, and over U1, 1, I also take A, and I take over U0, 1, I take E, and over U1, 0, I take E op. Where Uij is the intersection of Ui with Uj. And I have a multiplication which turns this into a Fell bundle. And now I can look at the associated C-star algebra, which is a continuous C of T algebra. So the functions on the circle act on this thing by just restricting to U0 and U1. Now you will say, hang on, these were open sets. How can I restrict it to that? Well, you can. Since this just has to sit in the multiplier algebra of this Fell bundle, this is OK. It is. And since everything inside the E and the A, where T had an action on T, this C-star algebra is also equipped with a T action. And if you look at what the fibers are, so here's my circle again. Here are the open. Here's the open cover. The fiber over a point here would just be isomorphic to A. The fiber here would be isomorphic to A. The fibers over these points here would be linking algebras. And now, how do I get from this to locally trivial bundles? I told you that these Fell algebras, these Fell bundles were not necessarily locally trivial. You can use a theorem from our paper. Which says that if you have a locally compact space with some technical assumption with finite covering dimension, and you have a C0 of X algebra, continuous C0 of X algebra, with fibers D tensor K for some strongly self-absorbing C-star algebra D. then I can find a locally trivial bundle of with fibers d tensor k over x. So I can find a bundle B such that this is isomorphic to the section algebra if and only if B satisfies the so-called generalized Fell condition, which was something like this. So for all x in X, there exists a closed neighborhood V and a projection P in the local algebra over V such that the class of P evaluated in a fiber represents an invertible element in the K-theory of the fiber. For all V in V. And this is something that you can check here. For example, if I'm here, I just choose a small open neighborhood and take the 1 in the algebra. That works. Here I have the linking algebras, which had the 1 in the upper left-hand corner. I can just take the 1 there and 0 in the lower right-hand everywhere else. This represents an inverted element in there. And I can find this for any point here. So in particular, you get such a locally trivial bundle after stabilizing this. So if I now take C star E tensor K, this is isomorphic to the section algebra on the circle of some locally trivial C star algebra bundle A over T with fiber D tensor K, where D is A. Sorry. And what happened to the equivariance? Well, you now have this. This is all non-equivariantly, but you had this action here, and this action was fiber-wise. This is an isomorphism as C0 of X algebras. So I can use this isomorphism to get a T action induced here. So I'm done with having a, so I can turn CTA into a T algebra. With fiber-wise T action. Well, you don't need these steps, really. This is just to make the connection with what I started with. My sort of proposition would be that you just forget about these and just work with the stuff that you get from the Fell bundles, because that's nice enough. OK, so this might be a bit boring and also a bit artificial, because we sort of inverted this thing here by brute force and introduced this UHF algebra, this tensor product of matrix algebras, just to make this work somehow. And in the last 5 minutes, I would like to outline there might be a construction like this over UN. Because there's an explicit description of this basic gerb over UN, which was worked out by Murray and Stevenson. So take UN as your group, define C to be the circle without 1, define Y to be the space of group elements and elements of the circle such that Z is not in the set of eigenvalues of G. And then take this has an order, since it's just it's homeomorphic to R. So you can tell what I mean by bigger and smaller elements. So I fix that order structure. So and this is the fiber product of Y with itself over G. And the other data that we need is we fix an exponential functor. F from category of finite dimensional complex vector spaces to itself. So what this should be is it is a functor which has the property that this natural transformation tau that I wrote down there provides an isomorphism between applying the functor to the direct sum and the tensor products of the results. And I also want an associativity condition. So there's a diagram involved there that I will not write down. And if you want examples of these, for example, I could take the total exterior power, or I could take just the top exterior power. This will also work. And another thing is I still need to invert something, but this time it just depends on the choice of this functor f. I have to, I define mf infinity to be the endomorphisms of f applied to c to the n, and then take this algebra, take the infinite tensor product of that. And so this y squared, this fiber product, is a groupoid over y. And y squared decomposes into 3 parts, which I will call plus, 0, and minus. And well, this is where this consists of points g, z1, z2, such that z1 and z2 satisfy this condition that they are not in the set of eigenvalues of g. And the plus part is the ones where z1 is smaller than z2. This is the part where z1 is bigger than z2, and this is the part where they agree. And I will concentrate on constructing, I want to construct the Fell bundle over this groupoid now. But I will concentrate on just the part y plus, which in itself is not a groupoid, but you have to start somewhere, right? And we define the fiber over gz1, Z2 to be the tensor product over all lambda that are in the eigenvalue set, such all eigenvalues in between Z1 and Z2. And now I apply F to the eigenspace corresponding to the eigenvalue lambda and take the tensor product with this absorbing C star algebra MF infinity. And this has the right multiplication, or this is a right Hilbert MF infinity module. And the left multiplication is Y an isomorphism. Well, I now need to look at the compact operators of that. So the compact operators is the anamorphism algebra of this thing here, tensored with that. But I can identify that, again, with this absorbing C star algebra, MF infinity, because that was the way that I constructed this. This absorbs end of F of any subspace. And I can do that in such a way that it satisfies the right associativity condition here, over Y squared plus. So what this gives me, what I end up with, is I have at least a multiplication where I form the tensor product over this algebra MF infinity there. Why is that? Because if I take the tensor product of the eigenvalues in between Z1 and Z2, and then the ones that are in between Z2 and these three, I can just collect all the tensor products together and get all the eigenvalues in between Z1 and Z3. And this was designed in such a way that I have this map over Y squared plus. And as I said, this turns out to be associative on this thing here. So I nearly get a Fell bundle, right? The only thing that's left is I need to check that I can extend it to all of Y squared. I know what to do there. I mean, over this part, this is the part where the units live, right? This should just be the C star algebra MF infinity itself. And here, I of course want to, or on this part, I want to take the opposite fibers, so the opposite Morita equivalences to those on this. And I have a definition of the multiplication extended also to Y squared. Yep. Can I just list the problems when I'm done? So this is nearly finished, but the big question is, I mean, I checked only the associativity over Y squared plus. Can I also extend it in such a way that it is associative over all of y squared. And then, of course, I mean, I know that this example works if you choose f to be this functor here, because then what I told you boils down to exactly this definition of the basic gerb of Murray and Stevenson. Okay, and that's a good place to stop. Thank you.
Questions?
I mean, do you know what the equivariant maps from UN to equivariant GL1 of Casey spectrum are? So if you want to check that your thing you construct at the end is non-trivial, how it is located.
Yeah, that's, I mean, yeah.
Do you know what the target?
No. Do you? I would like to know. This is the question, how do you classify these twists, classification? Which is the question, how do I get BGL1 of KU as a G equivariant spectrum, and then how do I compute the maps from the space, the equivariant homotopy classes of equivariant maps from U1 to BGL1?